Yeah, so my name is Freddy. I'm from IBM Research. That's a new research lab, and it's recently 2010. IBM Research started 3 new research labs, one in Dublin, one in Brazil, and one in Melbourne in Australia. And the one I'm part of is Dublin, and it's the Smarter Cities Research Lab. And so mainly is try to make sense on top of city data. So we have a lot of data from the city, from different cities, and we have collaboration with Dublin City and other cities in Europe. And we try to make sense on top of this data. And this data is big data. It's on different domains, transportation, water, energy, buildings, stadiums, I mean anything. I mean citizens generate data, and from this data you want to use it, and you want to kind of making sense and try to improve the way you kind of you achieve your way in the city. So that's one of the Smarter Cities objective in IBM. And also we have also part of different groups work on risk analytics, exascale, and hybrid computing. So it's again big machines. And the other lab in Brazil is much more about smarter planets, and Melbourne is much more about natural resources, life science. So for this talk, so I will briefly introduce what we're doing in IBM Research in Smarter Cities Research Lab. And so mainly we have plenty of different skills from different dimensions, like in artificial intelligence. So we have people from knowledge representation, we have people from machine learning, and we have people from data mining, from the database community, from distributed computing. And we try to combine all of these different skills and try to achieve the different problems the cities have so far. So it's about transportation, try to improve the transportation system in Dublin and various different cities. And you have issues about energy consumptions, and we try to optimize the way people are using energy, and we try to minimize the cost. We try to have different ways. So, and there's plenty of really nice challenges. That's real world challenges. And that's really, I mean, that's one of the reasons I left Manchester for IBM Research, is because all the data is in, I mean, we have access to all of these different data. That's big data, that's stream data, that's heterogeneous data, and there's a lot of challenges. And we have all of these different use cases and all of these different collaborations using EU projects and working with SMEs, we're working with government. And we have a lot of opportunities to do really nice and smarter things by using this data and all these computation things and all these computational intelligence, artificial intelligence techniques. And that's really nice environment working with. And, oops, sorry. So we are the Smarter Cities Research Lab, and our objective is not really to give a vision of what will be a smarter cities in 10, 20, 30, 40 years' time. It's mainly say, okay, we have all of this data, now what we can do with that? Can we do things better? So for instance, if you look at the picture on the left, that's kind of the picture. We have similar pictures of Dublin City people trying to understand the traffic system in Dublin City. There are plenty of different screens, and they try to understand the situation in cities and try to take actions and change the way the traffic light is going on in the city based on the rush hours, based these days some new events and so on and so forth. And that's done manually by people. There are existing intelligent things that do basic things, but mainly they have to kind of switch and change on the fly based on what's going on in the city. And that's far away from to be smart enough. And what we want to do is to try to understand what they are using, what is their technique, and try to do automation of this. And for that we need AI. We need AI techniques. That's what we need for that. And also, I mean, in the term of self-sufficient, sustainable eco-city, so how we can consider all these different eco-aware systems that now report information about the energy consumptions, and how we optimize all of this. And all of these are monitored by different devices. They use different protocols, they use different data representation, and that's again stream data, large data, and how you combine all of those, and how you make sense on it. And that's a challenge. And all of these needs and anticipatory leverage ICT technologies. And so it could be in transportation systems. You need to integrate and to consider the road networks. You need to consider how the buses are moving away, what is the traffic light situations, all the works and maintenance. So you need to consider various amount of different data from different systems and from different services, and you need to integrate all of these informations, and then you'll make sense on top of it. And for energy management, that's the same. And again, that's still the same picture. That's smarter cities. And in that context, we have a lot of challenges in the direction of public safety, environment management, telecommunication, water management, and all of these different are kind of isolated problems. And you have to make sense on isolated things, and we want also at the end to integrate all of this, and that will kind of provide the smarter cities picture. And at the end, what is it about? It's about big data. So, okay, that's kind of a buzzword of what big means, and it means many things in our kind of IBM terms. So it means fast, heterogeneous, noisy data. That's a lot of meaning behind, and this is what we have in different contexts. So I just went through a few piece of applications, and we have buildings, events, energy, water, traffic, and that's all about big data. And what I mean by big data, let's, for instance, go to the traffic domain, and we have different data from the Dublin bus. So we have information about 1,000 of buses, and they give back their locations every 20 seconds. And you have to kind of monitor these informations, and the way the people are doing, the way they were doing in Dublin City, they try to understand the data, and they have a few pieces of software that play with and that try to combine piece of information, but that didn't work out. And IBM used this kind of stream data to try to make sense on top of this data. And so that's only one source of data. If you think about it, that's one source of data, and that's already streams. And what you can do that is display information on a map and try to monitor the bus locations, try to monitor the situation of the city. But if you try to combine only this is only a small piece of data, try to combine with other piece of data like SCAD's data, give you information about the number of cars that are passing by different junctions, about the camera in the cities, about the weather conditions, about different events, then you can really do really smarter things. You can say, okay, there's a congestion right now, and because I detected through this Dublin bus data, then I can now infer that at some point there's a congestion because of X and Y, because there are some events, some weather information, some kind of bad weather conditions, and if you correlate that with historical information. So at the end, that's very nice and appropriate challenges that require combination of data, and that's big and heterogeneous data because they don't use the same format, and you have to deal with this, and they're not all static or all streams, they are anything, and they could be, and that's one part of the problem. But they are not only big and heterogeneous data, they're also sparse, so that's a map of, and we display on an hour window all the GPS location of buses in Dublin City. And you can see that there are some points where there are more sparse data, so you don't have access to a lot of information here. But in the city center, definitely you have much more, so you can, and you have to deal with this different sparsity of data, and you have to consider, okay, what can I infer from this data? And so that's one thing. And the other one is it's also noisy data. Okay, we have sensors from different domains, and then these informations could be accurate, could be not, and also could be noisy. So this display information about the speed of a buses. So some relevant, but that ones, you see a bus that go at more than 300 kilometers an hour if you trust the data and try to correlate information. So that definitely doesn't make sense. So you have a lot of this kind of information that say, if you use the data, try to integrate in the system, try to compute speed, try to compute different things, then you need to think back and say, okay, the data it's noisy at some point, and you need to kind of denoise and the data, and that's really challenging because you need to use semantic interpretation. You need to interpret the data behind, and that's one challenging task we went through. And also, it's not accurate. So again, if you display all the maps on the maps, all the bus locations, you see some points which are in the river. So there's a river in Dublin, which is the Liffey Valley, and you can see buses just swimming in that river. So is that possible? Definitely not. So again, the data is noisy, and you need to think where this point is part of. Is it part of the city? Is it just like a wrong point? And again, you have buses in some kind of building. So is it kind of a bus park, or is it just wrong data? And or is it because the GPS location consider different triangulations, and they give you back some GPS location right here? So you need to disambiguate the data, and there's different way to do that. And that's a research challenge. Try to understand what is the cause of the noisy data, and try to kind of denoise the data, and then try to get all the 100% of the data you ask for at the beginning, but at the end, the only one you get is maybe 30% of the data, because the 70% remaining is just noisy, not accurate, and you can't use it. And that's a challenge. And data is also irregularly refreshed. So so for some sensors, they give you information every 20 seconds. Okay, that's done, that's okay. But some sensors just have a strange or a weird behaviors, and you have to deal with that. That's also a challenge because of the nature of the data. And the same for, it's irregularly sampled, and based on because you have, for instance, in Stockholm, we tried to do some kind of prediction of the situation in the traffic system in Stockholm. And because the taxi, there's not that much taxi during the weekend. So it's Friday, Saturday. So you have much more. So it's during the week. So you have much more taxi at the beginning of the day and the end of the day. So you have much more data and information to process. While during the midday, you don't have that many information. And then that's again, you have a different sampling, and then you need to consider those as well. And so again, that was only traffic, so that's only transportation from different cities. We had access to the data, different sensors, but just think that's only one part, one applications, and we have all of those applications to deal with buildings, water, energy, public safety, and so on. And all of this data is big, heterogeneous, sparse, noisy, inaccurate, and that's all what city data is. That's what real data is. That's what the data we have. And why? It's mainly because the data come from the physical web, which is sensors, and the sensors don't give you accurate data, and they use different features, characteristics you have to consider with. So, and just to kind of give you a bit of publicity, so one part of our research group in Dublin also tried to push this data open, so then you can play with, and the community can do research on top of it and try to denoise data, try to making sense on top of data, and that's the platform we have. And then we expose the data weekly, the new data we have, and we have so far a few hundred data sets available, so you can play with and try to make sense on top of these data. And we have a few applications. So now I talk about data we have in Dublin City, and now I'm Dublin City and other cities where we have collaborations. And now I'll just go a bit more on advanced analytics, on what we did in terms of applications, analytics, research problem, and what we can do smart, and what are the research challenge. So that's kind of a picture that say, okay, look at the guy on the left, and he has access to a lot of data and information, but it just like, it doesn't really know how to use it. It doesn't really know how to make sense of it. And so that's a problem, and we have to try to understand the data, correlate informations, and then get further insight so you can detect anomalous behavior and then make action from that. So that's what we're trying to do in IBM. So mainly I go through a few applications, and also mention that which technique we're using and which research challenging we are working on. For the first thing we have to do is data assimilation. You need to get the data, and so as a simple example, in Stockholm City, so we have the GPS probes, we have the GPS location about truck of different companies and taxis, and we try to estimate the speed. Try to estimate the speed of this over the web, and that was challenging because you have to make sure that you have the accurate data. And again, as the same and in the buses, you have to you have to try to disambiguate the data at some point. And so we try also to do real-time traffic information and try to detect what is the traffic volumes at one point of time in a specific city, and then you can understand how the city is, what is the behavior of a city. And so we have different systems what they are using right now, and that required a lot of data analytics. And so for that, if you think about it, that's stream data, and you need to process data as streams, and you need very fast processing tools. And we did research in fast processing, fast computing, for processing a lot of streams very, very, very quickly and get insight from it, and then display information. And that's a challenging thing to do. And so that's an example. That's an application. The public transportation awareness, we're using it. The guys, the manager, the transportation manager, transportation engineers are using Dublin City to try to monitor data. So before they didn't get anything of this, they just tried to understand the situation, but it was not accurate. They didn't really put data together, and they didn't get information or knowledge on top of the data. And now they have tools for understanding what the speeds of what is the average speed of buses, or where the buses are, and where they could have congestions. And then they can take actions. Now they can say, okay, I have a situation right now of my city. I can take action of traffic lights and can change the strategy, because there are different strategies based on rush hours. And then if there are no rush hours, but you have accidents, then they can take actions. And that's one part to go, and then you want to integrate all those, and you will want definitely to have this kind of decision-making automatic. So you need to do this in an automated way, and that's part of the next challenge is how you do the integration together, and how you do intelligence, and where this is the place where artificial intelligence and computation intelligence really coming. That's where we go. We are able to kind of we can display information. Now we can really do much better. And here it's much more complex and analytics and modeling. So this is also again something we have experimented in Dublin City. And imagine you have a congestion on city, so you process streams of different buses in the cities, and then at some point you have some definition, some models of what is an anomaly or what is a congestion in the city, and then you want to say, okay, I know there's a congestion, it's an anomaly, my stream, there's something wrong based on historical information, based on just the previous weeks, the previous minutes, and then you try to detect anomalies, and then from these anomalies you say, okay, there's a congestion, what could be the causes? And if you look at only the streams, and a lot of community work on one streams, one source of data, and they try to compute patterns, they try to understand based on historical data what could be the next trends, but that simply doesn't work. You need to correlate these trends with other data. So it could be the weather information, could be events happening in the city, and you try to combine all of this, and all of those information give you the real explanation of why you get that output, what you get that which is congested, and that's really that's the challenging things, and you need to go through the streams to do fast processing, and you need to kind of combine different data and say, hey, here there's an event, and last week there were similar events, so that could be a potential explanation, and maybe that event doesn't really make sense, maybe that's an event which is 5 kilometers away from that road that could cause that congestion. That's, again, you need to interpret, you need knowledge representation for representing the data, for representing your model, you need all of this, and you need intelligent computation for that. So that was kind of just a map of an application. So you're congested, and then the people just click on the road, and they get a list of potential explanations scored with a probability to be that explanation. And also the applications understanding urban dynamics from digital source traces. So simply, everyone in the room, we either have a kind of a mobile, or we at some point we have a credit card we're using. We have digital traces that we can process, that we can use. We tweet, we use Facebook, we use different social media, and we are tracked. I mean, that's the world, and people and companies and university research can use that trace and try to detect patterns for understanding the cities. and they try to optimize planning, minimize operational cost, and they want to say, okay, because we can track people, we know their patterns, we know they're going to nightclub every Friday at that time, and so we know that we will need much more buses, we will need much more maybe public safety there, and that's where we use data from citizens. And so just one example, so it's mobile phone-based human mobility and interaction. So because it was an application in Boston and people, so they have a kind of, they can get access to mobile information. So they can know what is the pattern. So so this is a map of Boston. And in red, you have the patterns of people's during the week, what is the patterns? And at the end, you notice that high percentage of people use the same patterns. They first wake up, then they used to go to work, and then they stay at work, they stay around to go for lunch, and then they go back to work, and then, I mean, that's a common pattern, but there are different patterns, and they try to learn patterns from that different digital traces, and they will get very interesting results for try to design a city. So if from this information you can design new cities and say, hey, based on this pattern, because that kind of cultural people use this kind of patterns, and then you can display the cities in the way that you can do a nice planning of your city. And also we did some experimentation to understand how people talk together based on their geographical location. And that's an example in London that say that based on much more people of the South talk mainly all together, and there is not that many interaction with the people on the North. And if you think about why could be the explanation, it's mainly because of social and historical data. I mean, like in Dublin City, we have the same behavior, and people, I mean, much kind of much richer people live on the south than the poorest people live in the north. And then you can see this kind of clustering of peoples, and based on the way they interact together. And so the same for the US, they did the same, and they tried to see, we have the frontier between different states in the US, and then just try to figure out, let's forget about all these frontiers, and based on the people, the way they interact, is some frontier, are there any new frontiers, are there some kind of merging of states, and you can see that definitely some states like the Texas and here just like merge together, and there's a lot of interaction. So you can see different people are kind of closer, even if they are not in the same state. So you can design new frontiers from that, and you can, and then you can say if they interact together by mobile, maybe they go from one place to another place in the same state. So you need to think about what could be the best way to kind of provide transportation. Again, maybe you need hospital between, and that's the way you can use, and all of this is what it's behind. We use data mining, we use machine learning techniques, we use advanced AI techniques, and we had a lot of papers in the major AI community, and we do with proper research on that. It's not just like we take an algorithm, we use it, and that works. It doesn't work. That need to be applied. That need to be changed. That need to be evolutive as well, and that's why AI and evolutive AI is important. In my understanding. And again, another application, it's when you have an event, you try to detect where the people are coming from. And again, still based on the digital traces, you can display that if there is a Boston Red Sox vs Baltimore game, then you see on the red points give you the location where people are coming from, and the blue point is where the event is. And then if you change the events, and then it's a much more literature, much more cultural events, then you see that the people coming from to see that event is not part of the same area. And then, so you can really do prediction, you can improve event planning and management, and that's the thing. So you improve the way cities is managing. And if you improve it for those people, you improve also for you, because that's just like a domino effect. Okay, and in terms of prediction, so again, we have access to data in Dublin City, and we try to do predictions, and so mainly we made experiments, and we have an existing techniques a very basic linear regression approach for doing this. And so we take a line, we have so it was 18 kilometer long, 49 buses stop, and bus every 7-8 minutes. And on that graph, you see kind of the time they go for A, for the beginning to the end, and it change. And that's I mean, there's a 1 hour gap between both two, so that's huge. That's huge. And how you can do the predictions using that. So you apply different techniques, and then we tune and we change, and we provide, we do some kind of evolutive approach for doing this and for that. So simply use kernel regressions, and here it's an application on one we change and tune a bit the techniques for doing better prediction. And so as another application, if you look at Bing, so Microsoft Bing, if you want to go to point A to point B, I mean, it was to Cambridge, to Boston, to the airport. If you use those two systems, Bing and Google Maps, they give you at the same time two different paths for going from A to B. And that's because they use different algorithms behind, and there's plenty of variable you can play with, and there's different way of parameterizing your technique. And that just show that there's different techniques, and no technique is perfect. They just need to be aligned based on the context. And because they use proper and very basic data, if you think about integrating much more data, then you can provide much more prediction, and that's where we want to play. And as an example of why, so if you think about the shortest path, so the basic way of computing the shortest path between point A and B is to use Dijkstra and Bellman-Ford algorithm, and that works pretty well because they have an optimal structure property. So roughly, if you want to go to A and C, you need to make sure that if there is A, B, and C, then you need to take the shortest path for going from A to B. So that's a kind of a recursive process, and that's the kind of substructure property. But if you just change a bit the problem and say, I have a deadline, so I want to be there at that time, and from going to A to B and going to B from B to C as a standard deviation, so based on the time, and because there is uncertainty, so you have to play with. Simply these algorithms per se, like this, simply doesn't work, and you have to tune a bit the approach. Okay, so I'll go through a bit of transportation domains, and again, that's not only the focus of smarter cities in IBM research. I mean, in terms of data processing, if you want to understand what's going on in the city, you have maps, and then you want to detect in real time. So we have systems and software that in real time give you where the buses are congested, what is the current availability of bicycle, and what is the pollution on real time, because we have access to all of these data. And based on that, you have plenty of things you can try to correlate, combine. And also in water systems, and water system is much more about try to combine different sensors data, and all of these sensors, there's a lot of uncertainty and noisiness, and you have to deal with these informations, and uncertainties every year, that's kind of systems, and you have to deal with, and it's mainly you have a network, and you try to optimize under uncertainty. So there's a lot of research challenge with a lot of opportunity for doing very nice research and application there. And so as an example, we have a very sample of where we have valve informations, where valves are displayed on a water network, and you want to add one more, but so there's one, and you know that you have the consumptions, and you have some pressure, and roughly speaking, if you put some valve at different points, you can reduce the pressure. If you reduce the pressure, you reduce the leaks. If you reduce the leaks, you don't waste any money, and you save money for the different energy consumption provider, and that's a lot of money saving. So there's an optimization problem. You know the pressure, you know where are the leaks, and you try to put where shall I put that one. And we did that in that Shapelis.dma in Dublin City, and we had 44% reduction of the overall pressure. So, and then you have the cascading effects on saving money. And dynamic pricing, the same. You try so in Cork City, they have they do dynamic pricing. They want to do dynamic pricing, and that's very important because you have if you have a flat price, and at some point you have much more consumption of water, then you have to deal with this. You have to deal with this behavior, and then you will lose a lot of money here if you don't have a dynamic prices based on the way people are consuming water, and you need to have an adaptive way of doing that. Okay, so it was roughly kind of few applications, and we do really research in that domain. It's not just like we take data, we took existing research techniques, algorithms, we put them, and then we came with something new. That doesn't work. We need to apply and came with new research techniques and make evolution of existing AI techniques. And that was one kind of part of it. And if you think about it, that's just a small part. We just started the lab in 2010, and we have so many, and we're still growing and growing. And so that's okay. So that's more or less kind of conclude my talks. And so if you have to kind of keep in mind what IBM research is doing in the smarter cities context is try to making sense on top of big data, open data, continuous, fast, heterogeneous, sparse, noisy, not accurate data. That's the way real world is. And the objective is big and real-time data integration and analytics, and doing proper research, and using nature-inspired computation methodologies, and use evolutive artificial intelligence techniques. And we have some research paper in the top conference in that domains, and we really do research with real-world application, real-world data. And just one final slide, by the way. So IBM research is started in 2010, and we're still eyeing. And so if you have any interest in that kind of domains, and you have some kind of interest in that kind of presentation, and see, hey guys, I do that, I could see how it can fit. Okay, just send me an email, and then we'll be happy to kind of discuss with you that. Okay, that's conclude my talk. Thank you.